Okay, this is Physics 1C for Tuesday, October 13th. Tonight we're talking about a lot of stuff. We're in that period in Physics 1C where there's just all these different like applications of ideas that we're using. And tonight, kind of the theme is going to be looking at loops of wire and magnets, basically. That's mostly what we're talking about tonight. A couple things you should be able to do after tonight's class. You should have an understanding of how motors work, like a direct current motor. You should also understand, hopefully, how magnetic fields are produced. So up till now, we've talked about magnetic forces, but tonight we'd like to develop the idea of the magnetic field. We've talked about magnetic fields, but all we've said in the past is, like, suppose you're given a magnetic field that's 5 Tesla or something like this. We didn't describe precisely how you might produce a magnetic field of exactly 5 Tesla, so after tonight you should know exactly how you can do that. It's going to revolve around basically little wires carrying current. So that's mostly what tonight's about. Little wires that carry current and what kind of magnetic fields they produce. We'd also like to understand something about torque acting on loops of wire, basically. So we're going to start off with a little bit of a thing to finish up from last time. So last time what we talked about was the idea of the magnetic force on a wire alone. And we said that you could define... Oh, God. Really? Okay, so OneNote just crashed. It does that sometimes, I guess. So last time what we talked about was the magnetic force on a piece of wire that carries current, and we said we could define this force by taking the current flowing through the wire. We define a length vector that points in the same direction as the current, and you cross-product that with the magnetic field. And this allowed us to say things like, okay, suppose we have a magnetic field that points into the board, and let's say, near that we have a wire, and let's say that the wire is like right here, and let's say that it carries a current that flows in this direction here. So we have some current that's labeled as I, and suppose it has a length, and we just say that the length vector kind of goes that way. Then we can say that the force on this wire, can you guys tell me by typing in the chat, or can you all tell me by typing in the chat, what direction would the force on this wire be? There's a fly on my screen. Let's go get it. On this wire, if the current goes this way, and the magnetic field goes into the page, remember the X's represent into the page, what would the direction of the force on this wire be according to that equation right there? To the left, that's right, exactly. So this would give us a force acting on this system that would point this way. And the size of that force is proportional to the current, the length, and the field. So the longer the wire is, the bigger the force, the bigger the current, the bigger the force, and the bigger the field, the bigger the force. And this is, of course, produced because within this wire are little tiny charge carriers, and they're flowing in that direction, so they have a velocity in that direction, and they have some charge, and so really this force law is just an extension of the other force law that we learned about, which is the force on a single charge. So they're really the same idea. It's just that we know that something that carries current is just a bunch of charges that are moving, and we know what the velocity is, and we derived this left equation from the right equation, basically. Something I should mention is that this is often referred to, it's magnetic force, right? But you can combine this together with electric force to just get the net force acting on a particle. And what that looks like is this. So we have electric force, right? Which is Q times E. And now we have this magnetic force thing, which is V cross B. These two combined together, this is often referred to as, and maybe you've heard this when you've been studying or you've read it somewhere, this is called the Lorentz Force. It's named after a guy named H.A. Lorentz, who is a scientist that worked around the turn of the century. It's interesting. Okay, I don't want to go into too much detail here, but Lorentz is a very interesting person because he's someone that... Jeez, how far are you guys in Physics 1D right now? Are you talking about relativity yet? I know a few of you are in Physics 1D. Have you guys got to relativity yet? It's gotta be soon, right? You guys still doing... You start Wednesday. Okay, we'll get ready to start talking about Lorentz transformations. It's one of the things you'll discuss. So Lorentz was working on trying to understand... you'll learn more about him in relativity, but this is called the Lorentz Force. Okay, so it's possible okay, Ash is saying in the chat that it came up in 270. Is that a math thing, the Lorentz transformation? Laplace, yeah, it's probably Laplace. The Lorentz transformation is basically just a way of describing how you change coordinate systems between a moving coordinate system versus a coordinate system that's at rest. And it's different from... You've already learned about the Galilean transformation equations, which is basically taught in Physics 1A, and it's usually referred to as just relative velocity. Relative velocity? You know about relative velocity, right? And within relative velocity, you discuss how one person would measure someone's coordinate versus another person measuring someone's coordinate, and you get what's called the Galilean, transformation equations. I don't know. You might not have, like you said, used that name, but Galileo was the one that wrote them down first. But then Lorentz, along with a few other scientists, realized that those equations needed to be altered. And maybe I'm getting this wrong. So it's like maybe I'm wrong about this, but they realized that the equations needed to be altered because of electricity and magnetism. I think that's right. I may be wrong about that, but they realized that there was an issue with using the Galilean versions of the transformation equations when you applied them to electricity and magnetism, specifically to a moving charge. And that led Lorentz to come up with these newer transformations. And if I remember correctly, Einstein then used them because they happened to apply to special relativity. But the thing that Lorentz was missing was that, there's this thing called the ether you're going to learn about, and Lorentz was trying to use the ether to explain what was happening, and what Einstein realized was you don't need the ether, and that was the kind of groundbreaking thing that Einstein did. So Einstein was able to borrow from the work that Lorentz had already done, and it's not like diethyl ether. It's a type of, it's like a medium. It's a medium for for light waves. So historically, really getting really far off track here. It's all relevant, though. All this stuff is inherently tied together. You've been talking about optics, right? And we're talking about electricity and magnetism, and those two things are connected to each other. And then the idea of light waves and what they are is what we're ultimately learning about in this class. So all this stuff is connected, but the ether is something that was proposed to exist by scientists in, I want to say 17th, 18th, 19th century, somewhere in there, between the 1600s and the 1800s, the idea of the ether became popular. And it's spelled like A-E-T-H-E-R, not like the chemical. But you guys know about waves, I'm sure. You know about things like water waves. You've seen those if you go to the ocean. You can see them if you go to a pond in a park and you drop a rock in a pond, you see a little wave ripple out. You know about waves on strings because I'm sure many of you have either played a piano or a guitar or a violin, or if not, you've listened to them and you understand probably to some extent that the music that's produced by these instruments is produced by the vibrations of the strings, right, in stringed instruments. And then you know about probably sound waves too, because you hear sound waves when you hear someone in a room talking to you. So all of these types of waves have one thing in common. They have two things in common. They all have a medium. They have, in the case of water waves, they have water. In the case of waves on a string, you have the string. In the case of sound waves, you have, air, right? All of them have a medium, and then the wave is always produced by a disturbance within the medium. In the case of ripples in a pond, it's a rock that you drop in the water, it disturbs the medium, you get ripples, right? In the case of a guitar string, you pluck the string, and it vibrates, so you get a wave on a string. And in the case of air, someone talks or someone hits a drum, and then that propagates through the air, and you hear those waves hit your ear. So what about light? What about light? We thought for a long time that light was a wave. In fact, I suspect you guys are talking about interference in your 1D class, right? You're talking about interference? Are you guys talking about optical interference patterns and stuff like that? Okay. So in 1820, Young and Fresnel, they do this experiment called the double slit experiment, and they basically proved that light was a wave. They proved that light was a wave because they showed that it exhibited properties that really couldn't be explained by saying it was a particle. And up until that point, people thought, okay, it might be a particle, it might be a wave. Newton had a theory of optics that showed it as a particle. And then Huygens had a theory of optics that showed it as a wave, and Huygens' theory worked really well, and Newton's theory worked really well to describe the properties of reflection, refraction, as well as the way a prism works. But the problem was the interference experiment, and what you're saying, Ash, is right, that the double slit experiment basically showed that light must be a wave. So, okay, so light's a wave, right? And I just talked about other waves. I talked about strings and water and sound waves, right? And like I said, they all have this common thing, which is a medium. So for scientists in the 19th century, after this discovery is made, they say, well, it must have a medium, right? I mean, if it's a wave, it's got to have a medium, right? Does that seem reasonable to you guys? It makes sense, right? Okay. So if it has to have a medium, we better introduce one. And so they introduced this medium called the ether, and they said that it had some really interesting properties. They said that it kind of filled all of space, and that it had weird properties that it could kind of like pass through the Earth, or the Earth could pass through the ether, and it would be very hard to detect otherwise. But that was their definition of what the medium for light was the ether. And so tying this back to what I said before, Lorentz used this ether theory to basically salvage the transformations and to create his transformations between moving coordinate systems and all those kind of things, because he believed that the ether would create this force on particles that would cause them to compress as they moved. And so I may be getting some of the details of that wrong, but the big picture is certainly right. So people set out to measure this ether thing, and they use interferometers, which is a type of device that basically shoots light beams down two different channels and looks for an interference pattern between the two of them, similar to the interference patterns you're talking about in 1D. And they tried this experiment just over and over and over and over again. Okay, like multiple times at multiple sites. I believe some of the places they did them were at Mount Wilson. If you just give me a few seconds, Ash, like I'm not going to read that right now. Just give me a few seconds, okay? So they tried this experiment, and they tried to detect the ether, basically. They tried to detect the ether by using the Earth as a laboratory and trying to see if the Earth, if the speed of light was faster going in one direction versus another direction. And they found no evidence of it. So this theory that light needed a medium was kind of falling apart, and they started to have to think that maybe light was a type of wave that doesn't have a medium of any kind, and the ether theory was just wrong. And so that's where we are now, and that's what led Einstein to write down the special theory of relativity, was because he realized that was really important, that you don't need the ether. It's not necessary. And when you get rid of the ether, all kinds of really cool things happen. And that's what you'll be studying in 1D, and what you'll study in 1D if you go there next semester. So, all right, let me link what you read. Read what you read. Yeah, I mean, this just says the ether isn't real, right? As you mentioned. Yeah. Exactly. It's not real. We thought it was real, but it's not. Yeah. Okay. All right. So, all this was just because I mentioned this word Lorentz Force, and you'll look at Lorentz Transformations, and you can read more about that stuff if you want to. Lorentz has some papers that you could read. Okay, so last time we were talking about this magnetic force, to just bring this back home, and we said that it was derived from this idea right here. Now, what we'd like to look at is a particular setup. We did kind of a relatively simple problem with magnetic forces, but we're going to do a little more complicated one. That's this problem right here. We want to look at the magnetic force on a curved conductor. Last time we looked at the magnetic force on a straight conductor like this. And for this scenario right here, what we need to do is we're going to use a similar version of the equation, which is just going to be a little bit different here. The current I is going to still stay there, but we're going to kind of turn it into a differential equation that we can kind of integrate, basically. And we're going to say if I have a curved conductor, then I need to break that curved conductor into little tiny segments, dl. Kind of already shown here. I hate the way that your book kind of already has all this stuff here, but I can't draw a better picture than this anyway. And we're going to use this to analyze what's happening in this picture right here. So in this picture, we have magnetic field coming out of the board, all the blue dots. We have a wire, and that wire is bent into a semicircular loop right here, and then it has a straight line right here. And we're going to basically be finding what is the total magnetic force on the conductor. Okay. you can see the direction the current's flowing, right? All right. So it says in figure 2730, the magnetic field B is uniform and perpendicular to the plane of the figure, pointing out of the page. The conductor carrying the current I to the left has 3 segments. One a straight segment with length L, perpendicular to the plane of the figure. So that would be here. Wait, why is it inwards? Okay, so there's like a wire coming in this way, actually, is what they're saying. And the current goes in that way and then up this way. Okay, I think I understand that. It's kind of weird. And then a semicircle with radius r right here. And then another straight segment with a length L parallel to the x-axis right here. Find the total magnetic force on this conductor. We're going to do that using this equation. The force on the straight line is very simple, and we kind of already got that here. So the new thing here is we want to find the force on this segment right here. So what we do is we break up our wire into little pieces, indicated by this red shading right here. And we say that the direction of the current in that location is effectively tangent to the semicircle at that point. So we have this dl vector there. And then we think, okay, what's the direction of the force that's acting on this piece right here? So we've got a magnetic field coming out of the page. So if you point the fingers of your right hand along dl, face your palm upwards, you should get a force vector that points this way. Are you guys on board with that? Does that seem reasonable? Don't worry about df/dy, just look at just the big force vector here. Does that seem like it makes sense? We can try another piece just to kind of verify that we understand. So if I come over here and I look at a piece right here, the dl always points basically in the same direction as I, so dl would go this way. What direction would the force on this piece be? So point your fingers of your right hand in the direction of dl. Outward relative to what, Ash? That's kind of a little too vague. Can you clarify? Relative to this? Do you mean relative to the center? Up and left, yeah. Perpendicular to dl, basically, right? So the force in this case, we can use red, I guess. The force in this case would point straight along a line, straight that way. That would be your df. Okay. So let's use that here, but let's make some statements about what's going on. In general, there's going to be an angle theta that's made relative to the origin right here, and that angle theta is drawn in the picture right here, right? And what we can do is we can kind of calculate what this quantity is going to look like if we use some of these variables. So the first thing I would say is, how can we rewrite dl in terms of maybe theta and r in this case? It's an arc length, exactly. So what would dl be equal to in that case then? I forget the formula, okay. So it's going to be r times theta, but in this case, it's going to be d theta. It's just the little tiny piece right here. D theta. Okay. So we have to do this dl cross b thing. And we know that there's going to be this thing that shows up here. So let's start to rewrite this here. So we're going to get the magnetic force on our one little piece is going to be equal to, the current in the wire is a constant. We need to do dl cross b, but at all points along here, dl and b are at right angles to each other. Would you all agree with that? That the angle between dl and b, that they're always perpendicular? Just write it like that. They're perpendicular? Do you guys agree with that? dl is always going to be in the plane of the page, so it's guaranteed that since the magnetic field's coming out of the page, that they'll always be at right angles to each other. So we can reduce this dl cross b down to just basically dl times b. or in this case, just I replace dl here with rd theta. Times b. Okay. Yeah, because dl and b are perpendicular to one another, so yeah, we can just, it would be, you know, dl times b times sine of 90. Okay, now what else can we do here? I would say that if you look at the way that these forces are oriented here, this one this way and this one this way, it seems like the x components are going to point exactly in opposite directions to each other. Would y'all agree with that statement? So I think we can ignore the x components, and we can really just look at the y component here. And if we're just looking at the y component, here, let's make some space, then we just need to multiply by what? Sine or cosine of this angle right here. Yeah, so sine of theta. That'll give us just the y component, something that we've done. This is a pretty similar thing that's kind of shown up in both problems. Theta is this angle here, so the dy would be the opposite side, so that's why we're doing sine theta. And now I think we can just integrate this, because r is a constant, b is a constant, I is a constant. We're just going to integrate d theta, sine theta, d theta, right? So I would argue that the force, so the force, we get that from integrating this, should be equal to I, r, b, and then we're going to integrate sine theta, d theta. We're effectively, by integrating here, really what we're doing is we're summing up all of the y components, dfy here. And we would integrate from what? 0 is down here over to pi, I think, right? So we perform the integral. Y'all can do it yourself if you want to. Integral of sine, I think, is negative cosine. So that'll be, maybe we can write it over here to save some space. So IRB times, so negative cosine pi minus negative cos 0. I think it's going to be 2 IRB. Yeah? Y'all agree? Any questions? You're going to see kind of problems like this in the future. I think one of your lab manual will have problems. It doesn't have a curve, but there's a scenario where you have to remember to use this, where the magnetic field, I think, changes over some region. I'll show you what it looks like here in a second. But let's see. So let's just work it out. So cosine of pi is -1. So this is the negative of -1 minus -1. Well, that's a lot of negatives, but I'm pretty sure that's equal to 2. Yeah. Just checking to make sure. That's a good question. So there's your force. Oh, we needed to add to this. We want to find total, right? So we'd have to add to that. In this region here, the force is just going to be equal to, let's see, I is that way. So it's still going to be upwards, which they've already shown us. So for the straight portion of this, you're going to just get IL times B. So our net force, or the total force, would be 2IRB for the curved portion plus just I times L times B for the other portion. That would be our total force, and it would be up. By the way, I did this thing where we found the y component. If we'd done the exact same calculation for the x component, even the math would say that it's 0, because we'd be putting a cosine theta on here, and if we integrated cosine theta from 0 to pi, we'd get a sine, but the sine of pi is 0 and the sine of 0 is 0, so yeah. Okay. Anyone have any questions? Okay. Yeah, so if you have a situation where you have a curved conductor, you're going to want to use this equation. Or if you have a situation in which either the current or the magnetic field changes over some region, you'd also need to use this equation. The one I'm thinking about that's going to show up later in the class is going to be, suppose I have a wire that carries current like this, and I place next to it a loop of wire. It's a rectangular loop. We'll still call it a loop. And then let's say that this wire carries another current. We call it I2. We call this one I1 and I2. One of the things we can calculate for this one is we can find the force acting on this loop too, which will be, actually this problem is not quite simple. I'm thinking of flux actually, so, but regardless, something that will come up later. All right, any questions before we move on and start talking about the magnetic force on a loop of wire? All right, so for a loop of wire, okay, we just did this one. We're gonna grab this picture right here, and then we'll do this problem afterwards. So suppose we have a scenario like this, and I probably could have drawn this just fine, but I think this is a really good picture. So let's just take some time to look at it. Okay, so unfortunately there's kind of too much information here. What I want you to focus on is just this piece right here for now. So suppose I have a magnetic field that points to the right, and this field, it continues all the way through here, okay? So you have a uniform magnetic field that kind of just covers all of space within this region here. Near that wire, or sorry, near that magnetic field, we have a wire, and it carries current like this. It's a rectangular loop of wire that has dimensions A on one side and B on the other side here. And what we're going to do is we're going to think about what the forces on this side are, the forces on this side, as well as the other two. And we're going to try to understand what would happen if we put an axis through here. And we're going to find it's going to end up rotating. So first of all, let's look at this side right here, side 2. What direction would the magnetic force, so use your right-hand rule, what would the magnetic force acting on this wire right here be? And I'll remind you what it is. It's FB is equal to I times L cross B. You're saying inwards? Do people agree with that? So point your fingers in the direction of I, face your palm in the direction that B is pointing, and then curl from I to B. You should get into the page. I agree with that. It's kind of hard to do, probably easier to do if you stand up, but yeah, point your fingers down. You get, wait. I gotta stand up and try this to make sure. So you point your fingers down, the magnetic field is to the right, so you point your palm to the right, and then you would curl your fingers up. I think it's outwards. Take some time to think about it. You're kind of gonna have your fingers down like this. So this would be your hand. Your fingers are this way. Your palm is this way. And your thumb would be coming out of the board. God, that's really hard to draw these things. It's I cross B. Yeah, okay, that's right, Keanu. Inward would be B cross I, yeah. So I cross B is out. Ignore my horrible drawing over here. So on this piece, we say that the magnetic force is outwards. And it kind of applies to the entire wire. So we get an outward force like this. On that one. Now what about the one over here? The current's flowing upwards. Magnetic field is this way. Do I cross B? You're probably using your left hand, Mr. Meowers. This one's inwards, right? So just think about it like this. You point your fingers. This one's a lot easier to do. So basically stick your thumb into the board and notice that if you rotate your fingers from I to B, your thumb points into the page. Make sure you can kind of convince yourself of that. Point your fingers in the direction of I in your right hand, and then swing your fingers from I to B. Yep, curl towards the magnetic field. Does your thumb point inwards? Has to be your right hand. Your left hand will give you the opposite answer. Gotcha. Okay, so on this side, then we agree that the magnetic force is now this way. So inward here, outward there. And then on the bottom side, I would argue that there's no magnetic force because the current is parallel to the magnetic field. So we would get, for F3, you'd be doing something like I times L times B, but then you'd be multiplying by the sign of 0. And if on side 1 at the top, you'd be doing I times L times B times the sine of 180. And these are both 0. So you've got no force on the top and no force on the bottom. But you do have these forces on the sides. Okay? So now what we want to do is we want to take this entire picture and we want to look at it basically from down here. We want to do an edge view. So we flip it on its edge so that we're looking at side 3. So down here in this picture, this would be side 3 right here. And now the dots now represent the current. And this is side 2, right? So this is the current I flowing out towards you, right? Because if you take this thing and you flip it up on its edge, so you're looking at it from this side, I would be coming towards you over here, and it'd be going into the board over here. Magnetic field is still pointing to the right. But now what was before a out of the page is up. That's the force 2, and this one is down. And now we've added one extra thing here, which is this little piece here, because the idea is we're actually going to fit the entire thing on an axle that goes into the page at this point. It would be like an axle that would run kind of like this. And then we're going to look at the rotation that this produces. But before we do the calculations, can you all understand how this picture turns into the bottom picture? I'll give you a moment to kind of look at it and make sure. Okay, make sure you can kind of visualize what's going on there. So does it make sense then that you've got one force goes this way, one force goes this way, right? You said no because the force goes into out of the page? What do you mean? That's right, Mr. Meowers. Actually, regardless of if you can understand it or not, if you look at the second picture, one current is coming out and one current's going in. The forces have to be opposite to each other. That's a good way of putting it, Mr. Meowers. They have to be opposite to each other. Okay, actually, I don't understand your question. You said no because the force goes into out of the page. I don't understand what you mean by that. Or maybe you're answering somebody else's question. If one is going in and out, how does it move that thing upwards or down? On the picture up at the top, the idea would be that it would rotate up towards you and then back this way. And here that rotation turns into a clockwise rotation here. Okay. Good. So, let's look at this picture right here, and because it creates a torque, let's calculate the torque, okay? So we want to find here the torque on a loop. Okay, so for our loop right here, we're going to get torque, okay? What I'm going to first calculate is going to be what I call the maximum torque. And then we'll calculate the torque due to this orientation at an arbitrary angle. So in this position, the torque on side 2 plus the torque on side 4 is going to be our total torque. The torque on side 2 is going to be equal to the force, which is called F2, multiplied by the distance. Remember, this is how you do torque. You take the force multiplied by the distance to the axis. This is going to be our axis of rotation right here. So we multiply this times b over 2. That's the distance between here and here. Half of b, right? So from here to here would be b over 2. That's the torque in this case. For 4, the torque is F4 multiplied by b over 2. And we can calculate what these quantities are here by looking at the previous picture. I'm going to get rid of all this stuff because I expect you to kind of be able to reproduce that yourselves, and this picture's a lot clearer. So in this picture here, what would F2 be equal to? We get F2 by taking the current I, we multiply by the length of this wire right here. From here to here, the length is A. And then we multiply by the magnetic field, big B. And then we would also multiply by the sine of the angle between the two of them, which in this case is the sine of 90. And that would just be equal to I times A times B. If we go through the same calculation for F4, it's again the current I multiplied by the length from here to here, which is also A, multiplied by B, multiplied by sine 90. So they're both the same. So that tells us that in this case here, our total torque is going to be IAB times B over 2 plus IAB times B over 2. So half plus a half gives us 1. So the maximum torque that we get in this case is going to be I times A times B multiplied by the magnetic field. A and B are lengths. This is magnetic field. This is current. So that's the maximum torque that we can get. And you might notice something else that shows up in this equation that has another name that we could use. What's A times B? If we look at our rectangular loop, that has side A on one and side B on the other one, it's area, yeah. So we could just say that the area, the area of our loop is equal to A times B. So another way to write this would just be that the maximum torque ends up being IAB. Okay, that's interesting. It's current times area of the loop as the magnetic field. Now we're going to learn, well, I'll just tell you right now, that it doesn't even matter if it's a rectangle, actually. We chose a rectangle because it's just really easy to do rectangles, to find forces and to calculate torque. But it turns out that this would work even if it was a circle. Even if it was a circle, it would still, the maximum torque you would get would still be current times area times magnetic field. That's really simple, actually, isn't it? It's just, imagine you construct a loop, and you can measure the area, and say you know something about the magnetic field. We'll learn more about this later. And you can obviously produce current. You could exactly figure out what the maximum torque is. Really simple. It works for rectangular loops. It also works for circular loops. It also works for circular loops where you have a whole bunch of loops of wire that are wound together. So suppose we take the exact same arrangement we have right here and say that we add on top of our wire, not just a wire that goes like this, but suppose we create kind of several loops of wire that just keep going and going and going in circles. So what if we have n loops of wire? That would just increase the torque, right? As long as the current's all flowing in the same direction in all the loops, then that's going to lead to a maximum torque that would be equal to the number of loops times the current times the area and then times the magnetic field. This tells us that you could actually increase the torque simply by just adding more loops in here. You may know from opening up devices like motors or other electronic things that you may have opened up before, you may notice that when you look inside of these systems, there's all these loops of wire for some reason. Have you guys ever noticed that before? If you break open really any kind of electrical device, you'll often find little tiny loops of wire all throughout it. And part of the reason why is because more loops does more things for you. Has a lot of effects, as we're going to see here. In this case, it affects the maximum torque. Okay, so that's the maximum torque. What would the torque be if the wire was oriented differently? So for that, we need to draw a little bit of a different picture. And I'll probably draw a kind of simplistic picture here. So let's say that our wire right here is oriented kind of at an angle. Okay, so let's say it's oriented at an angle like this. So that's our loop of wire. It still has current flowing in the same directions it did before. We're going to have current coming out right here and current going in right there. The axis of rotation will still be right there in the center, and you'll still have the length b over 2 right here. But now, when we're looking at our forces, let's use the same floor they used in the picture. So before the force was going up like this, that's F2. It's not going to change directions. Here the force is going down like this. It's also not going to change directions. It's also not going to change size. It's going to be the exact same size here. What is going to change is going to be the torque itself. So let's draw one more line in here. Maybe I'll use pink or something. Oh god. Why didn't it? Shapes. Okay. Got one more line through here. And we'll just kind of like make sure it actually goes to the center. Okay, so suppose that the torque acting on the loop has now caused our wire to rotate a little bit, as it would, and it's rotated to this new position here. And let's say that the angle that's made here, we'll call it phi. It's going to be the same angle as over here. And then we've got this distance here, which is b over 2. And then I'm going to draw a couple more lines on here. We're going to drop a perpendicular line right here. We're going to drop a perpendicular line right here. Doing that because when we find torque in this case, what we're going to use is the fact that the distance between this point and this point right here is going to allow us to find our... Let me make sure I'm doing this right before I do this. To find the torque, we want this distance, right? Oh, okay, I know. Okay. We're not going to pick these angles. And I'll explain why in a second. Oh, no, don't do that. I'm going to have to go in and, like, just erase them. I want the other angle. And I'll show you why. The shortest distance to the center of rotation. Yeah, that's right. We call that the lever arm, right? That's this distance here. That side right there is L. Okay, I actually want this angle up here. I want the upper angle. And the reason why is going to become apparent here in a second. So I'm going to draw another arrow on here. And I want to make that arrow come from here and be at right angles to my... Okay, so I draw that in there. I'm going to make it have a right angle here. And I believe that this angle is also phi. Can you all see that? If the upper angle here is phi, it's easy to see in this picture. If this angle is phi, then that one inside of there would be 90 minus phi. So this angle would have to be phi. Can you all see that? Okay. All right. So what's L equal to in this picture? So if the upper angle is phi, and this is L, I would say that the lever arm in this case is equal to b over 2 times the sine of phi. And now, when I find the torque on this system, it's going to be equal to the same thing that we got before. It's going to be F2 times b over 2, but also times the sine of the angle phi. And then same thing for F4. That's our total torque now. Adding those together, we end up getting basically the same thing we got before, except it's just I times A times B, and now you have a sine of phi in here. Which tells you that the size of that torque is going to depend on the angle. At what angle are you going to get the maximum torque? Okay, and would you agree that if we go back to our original picture over here, that this is that vector that I drew in there, right? I'm gonna give this vector a name in a second, okay? But for now, don't worry about it. That's our vector, right? And this would be the position of maximum torque then, because it's a right angle. You get minimum torque when the system rotates until it's up and down, right? So if this system, if it rotates 90 degrees here, what happens to the torque? It goes away, right? There's no more torque anymore. So in this scenario, this kind of static scenario, placing this loop with this current flowing in it into this magnetic field would cause the loop to rotate, but it would only rotate until, here, let me draw something in here. The magnetic field goes this way, right? The loop rotates. This is, okay, pay attention. This is the part that will definitely help you for when you're understanding things in your homework, so pay attention. The loop would rotate until this vector points in the same direction as the magnetic field. Can you see that? Until phi is 0. When phi is 0, which means that this vector and the magnetic field line up with each other, it's not going to rotate anymore, right? Can you all see that? Now, it might, due to inertia, wiggle past that point, but that would basically be an equilibrium position for it, a stable equilibrium position for it, is when this rotates until it lines up there, until the wire is basically perpendicular to the field. Can you all see that? What do you think they are, Ash? Yeah, they're forces. Yeah, the force. If I was to draw an arrow to represent the torque, it would not be in the plane of this page. The arrow for the torque we'd probably draw at the center, and it would either come into the page or out of the page. I think you have a lack of understanding of what the difference between force and torque is. You might want to review. But torque, the vector for torque comes from, where can I write it? This. Torque is equal to R cross F. It's a right-hand rule thing, actually, right? So what's R? R would be the vector that would point. It's adding a lot of stuff to this picture. I don't really want to do it, but maybe I can add it over here. The R vector would point this way. That would be your R vector. That goes from there to there. And if you do R cross F, it points into the page. Actually, in both of these cases, it points into the page, because it's rotating in a circle. So the direction of the torque is also given by the right-hand rule. No, this is the axis of rotation right here. It's exactly the same as the picture on the left. It's not rotating about the black line. Oh, are we rotating the black line? Yes. The black line is the thing that's rotating. Yes, 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 yes. That's right. The black line is doing the rotating. That's right. Okay, I want to go back and emphasize something I said again before. This rotation that we're talking about, the torque that we're talking about, it's maximum when you start off like this. It's minimum, it goes to 0 whenever this green vector basically points parallel to the magnetic field. That's when you get 0 force, right? Okay, so I'm going to add in a couple more things here. So, just as I said before, you could maximize, you could increase the torque acting by adding more loops. So suppose that we add more loops right here. So we just like have more loops that are right on top of each other here. To get the total torque, you would have to multiply by the number of loops in front of this right here. Okay, so with multiple loops, you would get the torque would be equal to N times A, or I times A times B times the sine of phi. But what I'm going to do now is say that we're going to call, we're going to use this symbol here, mu. It's going to be a vector, and we're going to say it's equal to N times I times A. A is going to be the area vector of the loop. The area vector of the loop is effectively what I've drawn here, but I don't want you to think about that for now. What I want you to think about is that we can define this thing that we call, this is going to be called the magnetic moment. And we're going to say it points in the same direction as the area vector. The area vector is basically defined by the direction that the current is flowing. You can actually figure out what direction it points. I would say in this case the magnetic vector would point this way. The magnetic moment vector would point like this. Can you see that if you rotate point your thumb in the direction of out of the board, like this right here? So point the fingers of your right hand so that your thumb is pointing in the direction of mu, the magnetic moment, which comes out of the board. Can you see that your fingers of your right hand sweep in a, what is that, counterclockwise direction? Can you see that? So basically, if you sweep your fingers in the direction of the current, your thumb will point in the direction of the magnetic moment vector. If the current were to be reversed, the magnetic moment vector would point into the board. Can you all see that? It's also true here where you point your thumb in the direction of the magnetic field, you'd get the direction of the current that kind of is flowing right here, right? And it shows up in this equation as the number of loops times the current times the area. So we can combine these two together to say that the torque that acts on our loop is equal to the magnetic moment cross products with the magnetic fields. And that's a really simple relationship as long as you know what the definition of magnetic moment is right here. So to repeat what I said a moment ago, and this part of it is the most, you'll have no problem finding these formulas. You'll look them up on the internet or whatever you do. You'll have no problem finding formulas. So don't worry about the formulas here. What I want you to emphasize is that if you have something that has a magnetic moment, and what has magnetic moments? Well, loops of wire are the first thing we're learning about here, but there are other things that have magnetic moments too. For now, it's just loops of wire, though. And what these things do are that when you place the loop into a magnetic field, the magnetic moment will tend to want to align with the field. Does that make sense? Oh, yeah, sorry about that. This is really important. It's just something you're going to have to know when you're doing your homework. I'm assuming that's why motors have multiple poles? Yes. Magnetic moment is this. It's, I mean, you can think about it in two different ways. So another way you could think about magnetic moment is this. Suppose that I give you a compass, okay? And I tell you that the compass needle has a north side right here, and as indicated by red, and it has the south side right here as indicated by black, okay? So that's my compass needle, and it has a north side here, it has a south side here, okay? And let's say I take my compass needle, right, and I put it into a magnetic field. So I place this compass needle into a magnetic field that points this way. The external magnetic field, not the magnetic field of the compass itself, because it does have its own magnetic field. So I have an external magnetic field. I have a compass. I put the compass into the magnetic field. What does the compass do? Is it going to rotate to the left, to the right? Is it going to stay still? What's it going to do? It'll line up and go to the right. Everybody agree? Everybody agrees. It goes to the right. No question at all, right? So in a way, what you could say is that it's as if this compass needle has a magnetic moment that goes this way. And when you place it in a field, it's going to rotate and swing down to there. And it'll, once it gets there, it'll wobble a little bit, but it'll eventually, it'll come into equilibrium, and the magnet is going to, well, the compass will point in the same direction as the magnetic field. So look at this. A loop of wire is exactly the same. It's exactly the same. If I place a loop of wire in a field, and I allow it to rotate about some axis, the loop of wire is going to turn until the loop itself points in the same direction as the magnetic field, right? I know this is hard to think about. I know it's in 3 dimensions, and I also know there's just a bunch of math on the screen that probably throws you off, but really what we're talking about here is the idea that a loop of wire acts just like this. Does that make sense? The loop of wire acts just like a magnet. It lines up with the magnetic field. Keanu, your question... Okay, does anyone have any questions about what I just said? I'm going to answer Keanu's question now. Keanu's question is, did we specifically place phi above the right angle for the purpose of this example? Yeah. Yes. Yes. And specifically because... I've lost my mouse. I wanted to define this angle here. I wanted to define that angle right there. Because it's the... Look at it, it's the angle... Look at it, it's the angle between mu and b. It's the angle between the magnetic moment and the magnetic field, right? That's why we wanted to do it, because I knew that that's kind of where we were going. We wanted to define this here. Okay, so Mr. Biars, you're saying it has a tendency to move in a certain way. Yeah, exactly. So when you think loop of wire, you should think it's just like a compass needle. It's a compass needle where the way that the needle points is kind of like, you know, it points out away from the loop. So magnetic moment. This is torque. Anyone have any questions? You want to do a real quick problem? We'll do a problem, we'll take a break, then we'll talk about motors when we come back. Why does it hate when it does that? There we go. I'm going to write the equations we just derived up here. So magnetic moment number of loops times current times area of loop. This applies to not just rectangular loops, but also circular loops. And then torque Circular coil, 0.05 meters in radius with 30 turns of wire, lies in a horizontal plane. It carries a counterclockwise as viewed from above, so the current's kind of going like this. Current of 5 amps. The coil is in a uniform 1.2 Tesla magnetic field directed toward the right. Find the magnitudes of the magnetic moment and the torque on the coil. Before I do this, because I want to emphasize the conceptual understanding over just the math is easy, the concept is hard. Can you tell me, if this thing was allowed to freely rotate in this magnetic field, and let's say we do so by, I'll draw one extra line on here, but I'll erase it in a second. Let's say that we have an axis that goes this way, and that our loop is basically free to rotate around that axis, okay? Tell me, what direction is the loop going to turn? Is it going to rotate this way, or is it going to rotate this way? Everyone stop and think about it, and try to answer. Is it going to rotate to the right, or to the left? Clockwise. That's a good way of putting it. It's gonna rotate clockwise. It would be this one, right? It's going to rotate this way. It's going to rotate until this vector swings down and it points that, like, until that vector basically points this way. That's what's going to happen. That's how you want to think about this. So we know that the rotation is going to be clockwise. We know the rotation is going to be clockwise. Yeah, you said it right, Jesus. It's toward the magnetic field. This vector is going to tend to rotate down this way, and that vector is basically attached to this little ring, so the ring has to rotate until the open part of the ring, basically it rotates until the field is pointing straight through the ring, right? Until it's kind of just, yeah. Okay, so let's do the calculations. The first thing we want to do is to find the magnetic moment. So magnetic moment is number of loops, which is 30. 30 turns. You're going to see this come up a lot. When they say turns, it means number of turns of wire or the number of loops of wire, however you want to think about that. So it's 30, and we multiply times the current. There's not really a unit for this. Current is 5 amps right here. And we multiply with the area. So it's a circular coil. So we'll do pi times the radius squared. And that gives us our magnetic moment. Now it's a vector, so what I'm going to do is I'm just going to remove the vector part of this, and we'll add that in a second. We can just find the magnitude of this. I don't know what that is. Can you all calculate that for me briefly? Because we do need to take a break. We've been doing this for at least a little bit close to an hour now. So calculate that for me. All right, I got an answer. Anyone else get an answer? No response. I'm just waiting, so I can make sure that you guys have actually had time to take it in. That's what I got too. Yep. So I got 1.18, and then the units are just amps times meters squared. So that's our magnetic moment. And then the second thing we want to do is we want to find the torque on the coil. So to find the torque, we're going to be doing mu cross B. So in this case, magnetic field points to the right, mu points up. Let's define some axes. Let's call this the x direction. Let's call this the y direction. So then we would say that our magnetic moment would be 1.18 times j hat, amps meters squared. And the magnetic fields would be, we're doing cross product. So cross product with the magnetic field, which is 1.2 Tesla, and that would be times I hat. So we do j cross I. It's negative k. So the math is easy. The concept is what's hard. So I got, using those two numbers, I got 1.42, and then the units for this would be Newton meters, and it would point in the negative k hat direction. So this is consistent. This goes back to the kind of the question you were asking a second ago, Ash, about like, are these torques or are they forces? So can you see how in this case the torque points kind of perpendicular to both B and mu, and the fact that it points into the board. I don't know if that means anything to you, but in this case what it means is if I was to stick my thumb into the board, the direction that my right hand rotates would be the direction of the torque, which I don't know if that's easy to remember. What is easy to remember is that mu is going to tend to kind of rotate down until it points this way. So that means it rotates clockwise. So basically negative k hat is clockwise, k hat would be counterclockwise. Can you see that? So again, it's the right hand rule. You point your thumb in the direction of the thing, and that tells you, oh, that's a vector, basically. Does anyone have any questions? Do you feel like you understand the idea of torque acting on a coil? Yeah, it's definitely confusing. I don't disagree. I don't disagree. It's a lot easier just to think about clockwise and counterclockwise. Can you ask me questions over break? Sure. It's the same thing, dude. Yeah. Counterclockwise is positive, right? All these things, right-handed coordinate systems. It's not odd. It was designed that way. It's a right-handed coordinate system. Let me give you an example. If I tell you that you already know the answer to this question, but I wonder if you know why. If I tell you that the x direction is to the right and the y direction is up, can you tell me what direction positive z is? Is it into the page or out of the page? Out. You all know that. You all know that. Like, you don't even have to think about it because you just know, right? What happens if you do x? Take the fingers of your right hand and rotate them from x to y. What direction does your thumb point? It's out of the page, right? Yeah. I cross j is k. Right-handed coordinate system. We call this a right-handed coordinate system. A left-handed coordinate system, the z would be going in. All of these things, the definition of torque, the direction that the current loop goes, the torque equal to arc, they're all the same thing. It's all the right-hand rule. The force on a particle that's moving, the force on a current-carrying wire, they all use the cross product, so they're all related to the right-hand rule. And it's kind of really kind of essential. All right, well, I definitely need to give you all a break. I don't want to burn you out. So I'll stop for a second. I'll answer whatever questions you have, Ash, and then we'll come back. We'll probably start again in 9 minutes, so 7:20. That's what we'll do.